Hey everyone, ready for a deep dive into something really mind-bending?
Sounds exciting.
Well, today we're taking on nuclear fusion.
Oh, wow.
But with a twist, we're
Sure.
looking at a new approach. It's called the Stellarator.
Interesting.
And it's got scientists all abuzz.
I can see why.
So our sources this time, a
Mhm.
recent article from IE Spectrum.
Okay.
It's called Stellarators in AI, the Future of Fusion Energy Research.
Okay.
And then we have a supporting document called Nuclear Fusion's New Idea, an off-the-shelf stellarator.
Gotcha.
These articles point to some really, really exciting developments in fusion research.
Yeah, I mean, what's so captivating about fusion is its promise of near limitless clean energy.
Exactly.
It's essentially replicating the processes that power stars.
I know, it sounds like science fiction, right?
It does.
But we're going to break down why these sources have everyone so excited.
Yeah.
But first,
Yeah.
maybe just taking a step back.
Sure.
Why is fusion such a hot topic right now?
Yeah. Well, for decades, we've been searching for a way to generate clean energy that doesn't rely on fossil fuels or produce that harmful waste fusion. It offers that possibility.
Mm-hmm.
Imagine a future where we could power entire cities with the energy of a single star,
Wow.
all without the carbon emissions
Right.
or the risk of meltdowns.
Okay. That paints a pretty compelling picture.
It does.
But achieving fusion is notoriously difficult, right?
Yeah, it is.
What are some of those main obstacles?
So the biggest hurdle, it's really achieving and maintaining the extreme conditions needed for atoms to actually fuse.
Okay.
We're talking about temperatures hotter than the core of the sun
Oh, wow.
and pressures that are almost unimaginable.
Okay, so it's not just about building a machine. It's about creating this environment that's almost otherworldly.
Yeah, exactly.
Wow.
And then there's the issue of containment, right? You need a way to hold this superheated, swirling mass of plasma. That's where the fusion reactions actually happen.
Yeah.
And you have to hold it in a stable and controlled manner.
So that brings us to the Stellarator.
It does.
What makes it different from other approaches to fusion? Like, we hear a lot about the tokamak.
Right.
So how is the Stellarator different?
So stellarators and tokamaks, they both use magnetic fields to contain the plasma,
Okay.
but they do it in fundamentally different ways.
Okay.
Tokamaks, which are more well-known, they use a simpler donut-shaped design, but they rely on internal currents within the plasma itself to create the magnetic field.
Okay.
And this can lead to instabilities.
Right.
Imagine trying to balance a spinning top on its tip. Even the slightest wobble can cause it to topple over.
I see. Okay. Yeah.
Yeah.
That makes sense.
Yeah, though.
So how do Stellarators address that issue?
Stellarators use external magnets to create a twisted helical magnetic field, and it wraps around the plasma, providing more stable confinement.
Gotcha.
Think of it like a carefully woven basket,
Okay.
holding the plasma securely in place, even under those extreme conditions.
So it's like a more intricate
Yes.
and robust approach
Yeah, precisely.
to contain.
And because stellarators don't rely on those internal currents, they have the potential to operate in the steady state,
Okay.
continuously generating fusion power without the risk of those disruptive instabilities.
Okay. That sounds promising.
It is.
But if Stellarators are so great,
Hmm.
why haven't they been the dominant approach to fusion?
Right.
The sources mention that they actually predate the tokamak.
Indeed, yeah.
What happened?
That's a great question. Back in the 1950s, when fusion research was really taking off, tokamaks were simply easier to build. The technology that was available at the time,
Okay.
their simpler donut shape made them more straightforward to engineer. And they were initially able to achieve hotter, denser plasmas.
So tokamaks were the more practical choice back then.
Exactly.
For lab.
Really odd.
Okay.
But as research progressed, those internal currents in tokamaks started causing problems.
Ah, okay.
Scientists realized that even tiny instabilities could sabotage the entire fusion process.
Oh, wow.
And controlling those instabilities
Oh.
required complex and expensive systems.
So that's where Stellarators come back into the picture.
Yes.
Their more stable designs suddenly became much more appealing.
Exactly, you got it.
Okay.
But there was another challenge, designing and building those twisted magnetic fields. It was incredibly difficult.
Yeah, I can imagine.
Think about trying to sculpt a complex 3D shape with magnets. It requires an incredibly precise arrangement of magnetic coils.
Wow.
And even the slightest error can throw the entire system off balance.
That seems incredibly challenging.
It is.
So what changed? How did Stellarators make a comeback?
2 words. Computing power.
Okay.
In the 1980s, A physicist named Alan Boozer developed a mathematical framework called Boozer coordinates.
I remember that name from the sources,
You do?
but I have to admit I didn't quite understand what that meant.
Okay, imagine trying to navigate a 3D maze in complete darkness.
Okay.
Boozer's work essentially gave scientists a map and a flashlight.
Ah, okay.
His coordinates allowed them to model and visualize those complex, twisted magnetic fields for the first time,
Wow.
opening the door to designing more efficient and stable stellarators.
So it's like a mathematical breakthrough
Yeah.
that paved the way for real-world engineering breakthroughs.
Exactly.
I see.
And those breakthroughs led to the construction of successful, large stellarators.
Yeah.
The late 1990s and 2010s,
Okay.
like the helically symmetric experiment,
Mm.
the large helical device, and the Wendelstein 7X.
Hold on.
Yeah.
Those are some serious tongue twisters.
They are.
Are those all examples of stellarators?
Yes.
Okay.
And they've been critical in proving that Lyman Spitzer's original concept actually works.
Mm.
These projects demonstrated that stellarators could achieve high plasma temperatures and confinement times, and this reignited interest in this approach to fusion.
Okay, so we have these large, successful stellarators.
We do.
But our sources also mention this new kitchen table-sized stellarator from
Yeah.
PPPL.
Right.
How does that fit into the picture?
This is where things get really interesting. That tiny device built with off-the-shelf parts and permanent magnets, it represents a huge shift in thinking.
Okay.
It shows that stellarators, they don't have to be massive and expensive to be effective.
Right.
They can be built quickly and cheaply, allowing for faster research cycles and a more agile approach to experimentation.
So it's like a David and Goliath situation?
Kinda, yeah.
Or a smaller, more nimble approach might
Mhm.
actually be the key to unlocking fusion's potential.
It's a fascinating development for sure.
Yeah.
And it's not just about the size and cost, this new generation of stellarators. It's also benefiting from advances in artificial intelligence and machine learning.
Wait, AI is being used in fusion research.
It is.
How does that work?
So AI algorithms can analyze the massive amounts of data generated by these experiments, helping researchers identify patterns and optimize the magnetic field configurations for even better plasma confinement.
Okay, so it sounds like AI is giving fusion research a serious boost.
It is, yeah.
But before we get too deep into that,
Okay,
let's back up a bit.
sure.
The sources mention that PPPL had an ambitious Stellarator project
Yes.
called NCSX
It did.
back in the 1990s.
Mm.
That ultimately failed.
Right.
What happened there?
So the NCSX project, it was a build attempt to build the world's most advanced stellarator at the time.
Okay.
Unfortunately, it faced numerous challenges,
Yeah.
including cost overruns and technical difficulties.
So it was a setback for Stellarator research.
It was, yes.
Okay.
But even in failure, there are valuable lessons to be learned.
Right.
The NCSX experience taught researchers a lot
Mm-hmm.
about the complexities of stellarator design and construction.
Mm-hmm.
And those lessons were applied to the development of later projects,
Mm-hmm.
including that small, successful Muse stellarator. That paved the way for PPPL's latest kitchen table device.
Okay, so even setbacks can contribute to progress.
They can.
But what about those new Stellarator startups
Yeah.
that came out of PPPL?
Mhm.
You mean Stellarerex and Thea Energy? They both sound fascinating.
They are.
What are they working on?
So they're both pushing the boundaries of stellarator design in different ways.
Okay.
Stellarerex is focusing on simplified configurations to make stellarators even easier to build,
Mm-hmm.
while Thea Energy is exploring the use of planar electromagnetic coils, which could lead to more compact and efficient designs.
Wow, it seems like the race to fusion is heating up,
It is.
and stellarators are emerging as a major contender.
Absolutely.
That's really exciting.
It is.
And it's not just about the science itself. There's a growing recognition
Yeah.
of the economic and environmental potential of fusion energy.
Mm.
And that's attracting significant investment
It is.
from both government and private companies.
For sure.
Okay, before we get too far ahead of ourselves,
For sure.
I want to make sure we understand the bigger picture.
Okay.
What are the key advantages of Stellarator
Mm.
that make them such a promising path to fusion energy?
Right.
And why are they gaining so much momentum now?
Yeah, that's a great question to explore. And it leads us to a crucial point. Even if we crack the code of fusion, How do we make it practical?
Right.
How do we turn this scientific marvel into a viable energy source for the world?
That's a huge question.
It is.
It's not just about building a reactor. It's about making fusion energy reliable, affordable, and accessible to everyone.
Exactly.
So let's unpack that in the next part.
That's good.
We'll dive into the challenges and opportunities of scaling up fusion technology.
Okay.
And explore the potential impact it could have on our energy future.
Great.
Stay tuned.
All right.
Welcome back. So before the break, we were getting into some of the details about why Stellarators are having a moment.
We were.
But we also touched on a huge question.
Right.
How do we actually make fusion a usable energy source, even if we can figure out the science?
Yeah, you hit the nail on the head. Fusion has always been this tantalizing goal, this almost mythical source of clean energy.
Yeah.
But translating that into something that powers our homes and cities, that's a whole other ballgame.
Yeah. Okay, so let's break down those challenges.
Okay.
What are the biggest hurdles beyond just the technical ones of achieving and maintaining fusion itself?
Well, first off, there's the sheer scale of the undertaking. Building a fusion power plant. It isn't like putting up a solar farm or a wind turbine.
Right.
We're talking about incredibly complex and sophisticated machines that require specialized materials, precision engineering, and rigorous safety protocols.
So it's not just a scientific challenge.
It's not.
It's an engineering and logistical challenge as well.
Exactly.
Wow.
And then there's the economic side of the equation. Fusion research, it's expensive.
Yeah.
It requires massive investments in infrastructure, research and development, and skilled labor.
And right now, there's no guarantee that those investments will pay off anytime soon.
Right. That's the risk investors are taking. Fusion has been just around the corner for decades.
Yeah.
And while we've made incredible progress, it's still unclear when it will become commercially viable.
But the sources we're looking at today, they seem to point to this surge in optimism and investment.
They do.
We've got these new Stellarator startups.
Right.
And then there's Type 1 Energy aiming for a commercial power plant by 2029. That's only 5 years away.
It is ambitious, no doubt. They're betting on the idea that recent breakthroughs, combined with advances in computing power, will accelerate the timeline significantly.
Okay, but even if they manage to build a working power plant, there's still the question of infrastructure, right?
Right.
How do we integrate fusion energy into our existing grids?
Yeah.
How do we transport and distribute it?
Excellent point. It's not enough to just generate the power. We need to get it to the people who need it.
Right.
And that means building new transmission lines, upgrading substations, and developing the technology to safely and efficiently handle fusion power.
So it's like a massive domino effect?
It is.
Even if we solve the scientific puzzle,
Yeah.
there are all these other challenges that need to be addressed before fusion can truly make a difference. Wow.
And it's not just about the technology itself.
Right.
There are also regulatory hurdles, public perception issues, and potential geopolitical implications to consider.
That makes sense. I mean, new energy technologies always disrupt the status quo.
They do.
And there are bound to be winners and losers.
Yeah.
But let's focus on the positive for a moment.
Okay.
What are some of the potential benefits of fusion energy beyond the obvious one of clean energy?
Well, unlike solar and wind power, fusion wouldn't be dependent on weather conditions.
Right.
It could provide a reliable and consistent source of baseload power, 24 hours a day, 7 days a week.
That's a huge advantage.
It is.
And I imagine it would be much safer
Yes.
than traditional nuclear power, right?
Right.
No risk of meltdowns or radioactive waste.
That's the theory. Fusion reactions don't produce long-lived radioactive byproducts like fission reactions do.
Okay.
And there's no chain reaction to get out of control. Of course, safety protocols would still be paramount.
Right.
But the inherent risks are significantly lower.
Okay, so fusion offers clean, reliable, and safe energy. It almost sounds too good to be true.
It does, yeah.
What are some of the potential downsides?
Well, one concern is the cost of electricity. Even if we manage to build efficient fusion power plants, the initial capital investment will be substantial,
Yeah.
which could translate into higher electricity prices for consumers.
So affordability is a key factor.
It is.
It's not enough for fusion to be clean and safe.
Well,
It also needs to be economically competitive with other energy sources.
precisely.
Okay.
And then there's the question of tritium, one of the fuels needed for fusion.
Right.
Tritium is a radioactive isotope of hydrogen that's not readily available in nature.
Yeah.
We need to develop ways to produce it on a large scale, which raises its own set of challenges.
Okay, so even the fuel source for fusion is a complex issue.
It is.
But let's say we overcome all of these obstacles, the scientific, the engineering, the economic, the logistical.
Yeah.
What kind of impact could fusion energy have on the world?
The potential impact is truly transformative. Imagine a world free from fossil fuel dependence, where we can generate clean energy anywhere on the planet, without the limitations of geography or climate.
That's a powerful vision.
It is.
It could revolutionize everything from transportation to manufacturing to agriculture. It could even help us address climate change by providing a carbon-free alternative to fossil fuels.
Absolutely. And it's not just about meeting our energy needs. It's about creating a more sustainable and equitable future for all.
Yeah.
Imagine a world where access to clean and affordable energy is no longer a barrier to economic development or social progress.
Wow. It's hard not to get swept up in the possibilities.
It is.
But for now, it's still a long road ahead.
It is. What are the next steps in this quest for fusion energy?
Continued research and development is crucial. We need to keep pushing the boundaries of science and engineering, exploring new materials, optimizing designs, and developing more efficient and cost-effective ways to achieve fusion. And that's where those smaller, more agile Stellarator designs could play a key role.
Yeah, well, they could, yes.
By allowing for faster research cycles and more experimentation, they could accelerate the pace of discovery.
Exactly.
Okay.
And it's not just about building bigger and better machines.
Yeah.
It's about understanding the fundamental science behind fusion.
Right.
And using that knowledge to guide our approach. That's where AI comes in, helping us analyze data, optimize designs, and make informed decisions about the path forward.
So it's a multifaceted approach,
It is.
combining cutting-edge science, engineering ingenuity, and computational power.
Yeah.
But it's not just about the technology itself, right?
Right.
We also need collaboration,
Yes.
both within the scientific community and between governments, industry, and the public.
Absolutely.
That makes sense.
Fusion is a global challenge that requires a global solution. We need to share knowledge, resources, and expertise. If we want to make this dream a reality,
It's inspiring to think that so many brilliant minds are working together towards this common goal.
it is.
But let's shift gears for a moment
Okay.
and bring it back to Stellarators specifically.
Right?
We've talked about their history, their recent resurgence, and the advantages they offer.
We have.
What are some of the specific innovations
Yeah.
that are driving this renewed interest in Stellarators?
That's a great segue into some of the details we haven't had a chance to delve into yet.
Okay, perfect.
Let's explore those in the next part.
All right, sounds good. Okay, so we're back and ready to get into some of the really cool details about Stellarators.
All right.
Before the break, we were talking about how they're making a comeback in fusion research, thanks to some key innovations.
Yeah.
I'm especially intrigued by these smaller, more experimental designs we keep hearing about.
Right.
What can you tell me about them?
Well, they're really shaking things up.
Yeah.
Remember that kitchen table size Stellarator from PPPL we discussed earlier?
Yeah.
The one built with off-the-shelf parts? And permanent magnets.
I remember.
That's a prime example of this new wave of innovation.
Yeah, it's hard to wrap my head around something that small, playing such a big role in fusion research.
It is. It really challenges the conventional wisdom that fusion devices have to be massive and incredibly expensive. What's remarkable about these smaller Stellarators is that they allow for much faster experimentation and iteration.
Okay.
Researchers can test different configurations and ideas more rapidly, which could significantly accelerate the pace of discovery.
So instead of waiting years for a single experiment to run its course, they can try out new things much quicker.
Exactly. It's a more agile and adaptable approach to research, which is critical in a field as complex and challenging as fusion.
Right.
And this shift towards smaller, more experimental designs, it isn't limited to just research labs. It's also driving the emergence of those startups we mentioned, Stellarerex and Thea Energy.
Right. Those are the ones founded by former PPPL researchers.
They are.
What's so unique about their approaches?
Well, they're both tackling the complexities of Stellarator design from different angles.
Okay.
Stellarerex is focusing on simplifying the overall configuration, stripping away some of the intricate details that have traditionally made Stellarators difficult to build.
Right.
Their goal is to make these devices more practical and cost-effective to manufacture.
So it's like streamlining the design
Exactly.
and make it more accessible.
Thea Energy, on the other hand, is taking a different tack.
Okay.
They're exploring the use of planar electromagnetic coils, which are essentially flat coils arranged in a specific pattern.
Okay.
This could lead to more compact and efficient stellarator designs, as opposed to the traditional helical coils, which can be more complex to manufacture.
So it's like a whole new way of shaping those magnetic fields.
Precisely.
Yeah.
And it's just one example
Yeah.
of the kind of out-of-the-box thinking that's happening in the stellarator world right now.
Wow.
It's fascinating to see how these innovations are building upon the lessons learned from previous projects, including PPPL's NCSX, which, despite its ultimate failure, provided valuable insights that are now informing these new approaches.
It's a great reminder that setbacks and failures can often pave the way for future breakthroughs.
They can.
But let's not forget about the big players in the field, like Type 1 Energy.
Right.
They're still aiming for that ambitious goal of a commercial fusion power plant by 2029.
Yes, and their approach is heavily reliant on exascale computing.
Okay.
Think of it as the next level of supercomputing, capable of performing trillions upon trillions of calculations per second.
Wow.
This allows them to create incredibly detailed simulations of their Stellarator design, optimizing its performance and efficiency in the virtual world before they even start building physical hardware.
So it's like building and testing a virtual power plant before they commit to the real thing?
Exactly. And it's not just Type 1 Energy that's leveraging the power of advanced computing.
Right.
AI and machine learning are playing an increasingly important role in fusion research across the board. They're helping researchers analyze the massive amounts of data generated by experiments, identify patterns that humans might miss, and optimize those complex magnetic field configurations for better plasma confinement.
It sounds like AI is acting as a force multiplier for fusion research.
In a way, it is.
Yes.
It's augmenting human intelligence and accelerating the pace of discovery. It's helping us make sense of the complexities of fusion and guiding us towards more efficient and effective solutions.
Wow, we've covered so much ground today, from the history of stellarators and their recent resurgence to the cutting-edge innovations that are driving this new wave of excitement.
Yeah.
What are your final thoughts on the future of stellarators and fusion energy as a whole?
It's definitely a time of great optimism, but also cautious realism.
Okay.
We've made tremendous strides in recent years, and the momentum behind fusion research is undeniable.
Yeah.
But the challenges ahead are still significant.
So you're saying it's not a sure thing, but the possibilities are incredibly exciting.
Exactly. Whether it's Stellarators, tokamaks, or some other approach, that ultimately wins the race to fusion energy. The pursuit itself is pushing the boundaries of human ingenuity and scientific understanding.
Right.
And the potential rewards. A future powered by clean, safe, and virtually limitless energy are simply too great to ignore.
It's a journey that's worth taking, even if the destination remains uncertain. Thanks for joining us on this deep dive into the fascinating world of stellarators and fusion energy.
It's been a pleasure exploring this topic with you. And for those listening, remember, the quest for a sustainable energy future is a story that's still being written. Who knows, maybe some of you will be the ones to write the next chapter.